Good morning. This is the first part of the third lecture of the helicopter course. Today we will start to understand the hovering flight. We will study the actuator disk theory and we will derive the induced velocity down in the wake. Why can we hover with a helicopter? Don't forget, hovering is a balancing act of the rotor. Namely, the moment due to centrifugal forces is balanced by the moment due to aerodynamic lift. The centrifugal force is usually 20 times bigger than the lift force applied. The actuator disk theory or momentum theory was developed by Betts in 1920 as an extension from the ship propellers theory initiated in 1865. It is the simplest method for deriving the power required to hover. Assumes that the propeller is a rotating disc and imparts axial momentum to the air passing through it. The main simplifications made in this theory are: the rotor is assumed as a disc infinitely thin and uniformly loaded. The pressure is constant on the rotor surface. The pressure on the skin tube gives no contribution to the axial pressure, the D'Alembert paradox. This paradox says that in an incompressible flow produce no drag on an object surrounded by such a fluid, yet it does produce lift. The air is assumed a perfect fluid and non-viscous and incompressible, and we assume laminar flow. The main conclusion of the actuator disk theory is that the wake is contracting. The velocity of the flow, the air, it is accelerated at the level of the rotor, and down in the wake it is contracting. The velocity down in the wake is twice the induced velocity at the level of the rotor. For this, you will need to have a look at the demonstration of the actuator disk theory for hover. There are experimental proofs that the wake is contracting below the disk. You see here two experiments, one of a rotor rotating, hovering out of ground effect, and a rotor hovering in ground effect. In both cases, you see this contraction of the rotor. Also, the visualization of the tip vortices by moisture condensation shows the contracting of the wake. Here you see the tip vortices on a Lockheed Cheyenne helicopter at high altitude. The equilibrium in hovering flight shows that the thrust equals with the weight of a helicopter. Therefore, the fuselage is immersed into the flow, and the vertical fuselage drag, it is only 3 to 5% of the weight, and it is usually neglected. From the actuator disk theory, one can deduce the induced velocity in hover. You will have to look first at the demonstration of the actuator disk theory. Here we apply two principles: the principle of conservation of mass flow rate, m dot, and the principle of conservation of momentum. From the first one, the mass flow rate equals with the rho density, P number, R radius of the helicopter squared, times the induced velocity at the level of the rotor. From the momentum conservation, the thrust produced on the rotor is the mass flow rate multiplied by twice induced velocity at the level of the rotor. Substituting this into the thrust force, it results in the expression for the thrust in a hover in an actuator Blake disk theory. And therefore, induced velocity in hover can be easily calculated as a squared of weight divided by 2 rho p r squared. Therefore, if we know the weight of a helicopter and the radius of the rotor, we can have an idea about the induced velocity at the level of the rotor in hover. There are some important design parameters associated in this formula. The first one is the disk loading. Disk loading is defined as the ratio of the weight by the area of the rotor, PR square. It is equivalent with the wing loading that you have learned in the previous years. You also learned that wing loading affects the stall speed, the climb rate, the takeoff and landing distances, and turn performance. For a helicopter, the disk loading is affecting the hover capabilities and the power required to hover. Examples of disk loadings. Here you have for the military helicopters and for the utility helicopters as a function of the maximum takeoff weight. You see that for the military helicopter, the Bell 209 has almost 30 kilos per square meters. The Comanche RH-66, it has a disk loading much higher of 50 kilos per square meter. And in this way, you can see the K52 or K29 with quite high disk loading. There is also a difference between the Russian helicopters and the American helicopters. You can see that for a much higher maximum takeoff weight, the disk loading of the Russian helicopters is lower. What is the comparison between the wing to disk loading? If you represent this loading in pound per square feet as a function of, again, the gross weight, the fixed wing planes have loadings of 40 pounds per square feet. And the helicopters, you see them with loadings of 15 pounds per square feet. How important is this to the designer? It depends much on the helicopter operations. In this figure, you see the representation of the induced velocity down in the wake, so twice the induced velocity at the level of the rotor, as a function of the disk loading. You can also see that as the disk loading is increasing, therefore the rotor is becoming smaller and smaller, the velocity in a full developed wake is increasing. For R22 Robinson, you have velocities of 30 knots, which is a strong breeze. In an Apache H-64, the velocities are of 50 knots, which are a strong gale. And so forth, if you are reducing the rotor diameter, you arrive at the velocity down in the wake of a hurricane, 80 knots. A small rotor, a high disk loading, is inducing a strong downwash, a strong wake velocity. This can create visibility problems while hovering, the so-called brownout problems. Therefore, using a smaller and smaller rotor means saving more and more empty weight, but it has a practical limit. For example, this is a Huey hovering in dust. You can see the limitation in operating. The V-22, it was said, the tilt rotor, that it was landing naked Marines. The V-22, it was generating 3 times more downwash as a normal helicopter. For the 80 to 90 knots downwash was so strong that sea rescues were dangerous as the brownout was inducing a visibility of 0. In early testing, Marines literally had their clothes ripped off when making a combat entry. So, the procedures has to be redesigned in order to avoid flying naked. The evolution of disk loading in 60 years of helicopter development shows that the disk loading has been reduced. The trend has been to increase the disk loading to contain the dimensional growth, so reduce the empty weight fraction. The disk load increasing means a reduction in rotor radius. This is the end of the first lecture on hovering flight actuator disk theory.